Hey guys, it's Darius. Welcome back to InventBox, where the solution is right around the corner. We've been learning how to use matrices to move objects around within our world, and also how to apply a perspective transformation, make things look more 3D. Now at some point we're going to have more objects in our world than what will fit on screen at once. And we would like to be able to look around and see what's out there, look up, look down, to the right, or behind us. Essentially, we want to move our camera to view a different part of the world. But first we have to ask, where is our camera to start? Where are we at? Well, it's at the world origin. 0, 0, 0, X, Y, Z, and we are looking into the negative Z direction, which means that as our object moves in the negative Z direction, it appears to get farther away. Now first, let's position our box some amount in the negative Z and also a little to the left, which would be negative X. We'll be able to see the front face of the box and a little bit of the right face. And we can do this right now. It's the same as what we've been doing. We're just moving our object around. We just translate this guy. And I think I said negative 1.5 in the X and negative 2. That ought to do it. And there we go. Next, we will move our camera 3 units to the left so we can see the left face of the box and the front face of the box. And we'll also move it in the in the positive Z, like 1 unit. So move it back and to the left. Something like this, the purple arrow. This is what we want to do. However, recall that our shader program, WebGL, expects our shader program to output coordinates between -1 and +1 in the X, -1, +1 in Y. And so we don't really have a choice of where we're looking at on the screen. All of the vertices that are going to be visible have to end up within that box. So instead, we calculate the transformation of where our camera would be, and then we take the inverse of that, and we apply it to all the objects in the world in such a way that it would shift the camera back to the origin. All the objects follow with it and maintain the relative position between the camera and the objects. But then this is actually feasible because the camera is at the world origin like it has to be. We'll store our object transformations in a separate matrix from the camera transformations. Say you had 100 trees. Each tree would have its own XYZ translations stored in its own model matrix, and then you would have one view matrix to store the camera transformation, and then you would invert it and apply it to each object. I'd like to implement this now. So the first thing I'm going to do is rename matrix to model matrix and be more specific. Again, model matrices are transformations applied to your objects, moving them around in your world. Create another matrix called view matrix. Now if you're counting, you'll see that we have currently 3 matrices for different purposes. The model matrix and the projection matrix to apply the perspective, and then the view matrix to simulate a camera. And I say simulate because it's all it's actually just math. So now I want to translate my view matrix to the left and back. And don't forget to invert it. I cannot remember whether it's inverse or invert. We will find out. I think it's inverse. So now what we want to do is multiply our model matrix by the view matrix and the view matrix by the projection matrix to get our final matrix. But we can only multiply 2 at a time, so let's create an intermediate called a model view matrix. And model view matrix will be the product of view matrix and model matrix in that order, because it's going to start with the transformations in model matrix and then apply those in view matrix on top of that. And finally, we'll multiply projection by our model view, and our final matrix could now be called a model view projection matrix, MVP. And you might actually say that it is the MVP of the matrices because it's the one that we give to the shader. So now let's find out about if I chose the right. No, I did not. There we go. Okay, so just a wrap up that you do not move the camera really at all. You can't move the camera because at the end of the day, WebGL will render what is in that -1 to +1 box right in front of the screen, and the perspective matrix messes with that a little bit, but ultimately your camera is going to be looking into the -Z right in front of the origin. Instead, you calculate your camera transformation and apply the opposite to all the objects in the world, and you maintain that distance between the camera and your object, and you still see the same thing. Because it's math, we can do what we want and get the result that we want, and it doesn't really matter. I hope that this video helped you understand a bit more about how the camera works in computer graphics, WebGL. If you still have questions, please leave them in the comments. Thank you for watching. I'll see you next time.